Hello and welcome everybody. Good morning, good afternoon, good evening, and thank you for joining. Hi Dave, how is it going?
Good, and yourself?
Yeah, pretty good. Looking forward to this episode today. So this is number 4. It's amazing already. Number 4 of Road to Nodes workshop series. So we did a couple of good workshops over the last week and a half. So if you missed any of these, they are on YouTube as of now. So you can dive into the intro session we did last week, healthcare analytics also last week, and yesterday Matt and team did an amazing session on Apache Hop and creating workflows in Apache Hop for Neo4j. So that was pretty interesting. And today, different topic, different, little bit of a different angle, I would say, on the whole graph thing, with blazing fast graphs, hands-on with Apache Arrow and Neo4j. So I'm looking forward to this. Should be fun. Before we dive in, and if you watch any of these previous Road to Node sessions in the past days, you probably know what's coming, but I'll repeat myself no matter what. It's Nodes in November. So in a couple of weeks, we do run Nodes 2022, 16th and 17th of November. So it's a 24-hour live event. So if you're worried, oh, I won't be able to join this live because I'm based in this and that country, don't worry. We have it run 24 hours around the world, basically. So no matter where you are, you can watch something live in your daytime. No early or crazy late time needed. So that's going to be fun. It's going to be interesting. A lot of good content, lots of great sessions. So the agenda is building as we speak, but it's more or less there. And if you register now, you can have a look at it already. You can have you can start to build your agenda and all of that. So please put the link in chat again. Don't miss this. You would like to definitely not miss this, and therefore please register for it. If you have registered for any of these workshops, you're not automatically enrolled for Nodes, so you have to register separately, I'm afraid. Yeah, and that's what I have to say on this. So please keep this in mind. We will record this session as the previous one, so don't worry. We will share a link with you in the coming days. We will share some of the material that Dave will go through, also either links or slide material. So you will also have a, can have a look at this later on. We have a great team of colleagues, namely David and Shiny in chat. So if you have any questions, anything that's not clear during this workshop, please don't hesitate. Either type it in chat, or better yet, use the Q&A function in Big Marker for your questions, so we can have a look at those and answer you directly, so they don't get lost in the chat window. If time permits, Dave and I, we quickly had a brief chat about it. So if time permits, we can also answer some questions live during this workshop. But take the opportunity to use the chat function and the Q&A function for anything else. If you just want to say how cool you think this is and how great you think this session and the workshop run from Dave is, then also please use chat function. I'm glad to relate this praise to Dave either later on or during the session. So yes, I think this is what I had to say. Again, looking forward to this. Enjoy, everybody, and yeah, over to you, Dave.
Perfect. Let me see if I can share some slides here. Dun, 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 dun. Share my.
I always like to see
browser
I
tab.
see people from the UK, from Seattle, Florida, Montreal, San Diego. So yeah, it's cool. Thank you for joining. Somebody from Mexico as well. So really good to see. And here are your slides. Okay, perfect.
There we go. Perfect.
There we go.
So if I switch into slideshow mode, voila, great.
Looks good.
Greetings, everybody. A little bit about myself. I'm Dave Votila. I'm based in Vermont in the United States. I'm usually chasing 2 of our golden retrievers around, either the yard or the house. And I've been with Neo4j now for about 3 years or so. I've presented at a couple different events of ours, including the first Nodes conference a couple of years ago. You can find me online on GitHub or LinkedIn. Feel free to go check out some of my contributions there, or connect with me on LinkedIn. And outside Neo4j, you can find me on Twitter, and I also contribute to the OpenBSD operating system project. So if you're interested in operating systems and hypervisors and whatnot, that's usually where I spend my spare time. But today we're going to talk a little bit about Apache Arrow for ingestion. And the way I like to talk about this with respect to, quote, blazing fast ingestion is first focusing on, some of the myths around how it works and how ingestion and data ingress and egress with Neo4j works. But then most importantly, talking about the problem statements. So like, why should you care about this topic space? Why should you bother, understanding what we're going to go through today and going through the exercises, et cetera. Talk a little bit about some of the success stories we've seen in terms of like the performance uplift and throughput, and then show where kind of Arrow fits as a whole in the Neo4j kind of platform, if you will. We'll be doing some hands-on exercises as well once we go through this initial kind of introduction. Don't worry if for some reason you can't access them. Most of it will require access to Google. So if you're joining from a corporate VPN that might have blocked access to different Google Cloud services, might not work for you today. Or if you're on a kind of a low bandwidth connection, we'll be using Google Colab as well as a server I stood up within GCP to work through some of the exercises in the notebook. A quick check though, on the AV side, my self view is flickering. Is that coming through as a weird flickering video for everyone, or do I look okay?
You look okay. I don't see flickering either
Okay,
on the back
it's
end
probably
here.
just
Or
my side.
yeah. No, all
Perfect.
good.
So back to it. So when I talk about Apache Arrow and Neo4j, I like to talk about, first of all, who's the audience that should care about this, and ideally will, benefit the most from this conversation. At Neo4j, we talk a lot about developers and data scientists. If you look at what the Nodes conference stands for as an acronym, we're talking about developers and practitioners. I found this cute little kind of diagram of the quote, data science process via a Towards Data Science blog post. It's, real data science isn't linear, but this is kind of like a nice way to look at the different phases and the different stakeholders involved. And traditionally, we've talked about developers at Neo4j. Now we're talking about data scientists, but there's all these personas that really support this entire life cycle. And the folks that really benefit the most from understanding how Apache Arrow fits in with Neo4j are really the data engineers and the ML engineers, the folks that are responsible for putting the plumbing together, bringing the data into the graph, supporting the data scientists in getting their data sets loaded, populated, productionizing any of the workflows. Doesn't mean that data scientists or data analysts can't benefit from understanding this. As we go through the exercises, you'll notice that depending on what your role is, there are different ways to consume the Apache Arrow integration. And some of it, you won't even realize you're using it. It's helpful to know it's there. And you might actually see how this kind of empowers the data science kind of experimentation workflow as we go about it. And so the first of the two kind of core problem statements, they're really the two different sides of the coin here, ingress and egress. So problem number one is really traditionally reading graph features at scale has been hard. What do I mean by hard or graph features? So when we talk about graph features, we're talking about all the outputs from an analytics process on your graph within Neo4j. So generating things around maybe risk scores, could be just the outputs of centrality scores like PageRank, could be community IDs from when you're trying to cluster or identify communities within the graph, or something more complex like a node embedding, which is really a vectorized form of a feature. It could be basically any sort of metric or data point or complex kind of thing you generate from the graph that you're going to use in your analytics workflow. Typically, this is done globally at scale. That's what our graph data science platform is all about, is doing this across the entire graph globally in parallel in an efficient manner. But typically, people need to get this data out and operationalized in their existing platforms. And so even if you take a modestly sized graph, so I'm talking, when I say modest, I mean millions, tens of millions of nodes and relationships, generating things like node embeddings. So, let's say 256-degree floating point vectors for each node in the graph. If you were going to use traditional approaches of taking a Python driver, writing some code, and just saying, okay, let's just read these back out of the database, you're going to find that it's not really conducive to that workflow. Our drivers are really good for applications that need concurrency of transactions and transaction management. They weren't originally designed to do this large ingress egress of just a single data set at once with a single reader or consumer, if you will. And this is important in the data science kind of workflow because, to me, it's always important to understand this concept of expectations from the standpoint of the user, the data consumer, whoever it is, whether it's a data scientist, data engineer. The way I kind of look at it is, it's not that it's bad if something's slow, it's bad if something's slow and the user was expecting it to be fast. It's good to kind of maybe have it be the inverse of that. If I expect it to be slow, but it turns out to be fast, that's great. But if I think it's going to be fast, I can just do this and iterate quickly and experiment. And I'm finding, okay, it's taking a long time. I have no indication of how long this thing might run. That's where I tend to get frustrated personally. I'm sure we've all been there. So I kind of came up with this idea of this hierarchy of how people measure time on the scale from, is it interactive enough to be used in like a REPL? So can I use this interactively, like in a command line, for instance? Or is this something I know I need to run on a Friday afternoon because I'm about to leave the office and go away for a long weekend and I expect to come back in on Monday and see what the results were? And so traditionally, folks that I saw taking things like our Python driver and trying to, let's say, dump 10 million node embedding vectors out of the graph found themselves really kind of at the bottom of this pyramid here. So typically long running processes, struggling to parallelize them to get better throughput, and really kind of unsatisfied with effectively the progress. And where we ideally want to be, best case scenario when we talk about speed and performance, the higher up this thing we can go, the better. The more interactive and real time it can be, the shorter the iterations in an experimental process you can have. And as a data scientist or even a data engineer prototyping your pipelines, getting quick feedback, for anyone who writes code, quick feedback is essential to kind of the flow that you hope to achieve and getting productive and cranking out whatever you're trying to build or the kind of results you're looking to generate from your experiment. So understanding, is this thing I'm about to do going to be interactive enough I can just sit there and type, or should I run it and maybe go refresh my coffee cup? And if you're interested more in like a quantitative comparison between these things, I had done some experimentation early on when we started to release our Apache Arrow support, and found that it's orders of magnitude faster to take the Apache Arrow approach for large-scale egress than it is to try to just use the naive Python driver approach. So data scientists doing some functional testing or data engineers trying to just kick the tires on, maybe coming up with an idea for a workflow around Neo4j might be functionally successful with the Python driver, but when you go to scale it up, let's say in this case, it was just shy of 2 million node embedding vectors being retrieved by a single reader. We are talking multiple orders of magnitude faster using the Apache Arrow approach. Well, you can reach for things like our Java driver or even maybe C# and get a little bit better performance just because of the differences between the runtimes with Python. It's still orders of magnitude faster using Apache Arrow. We'll get into the reasons why, but if you think about back to this kind of two-sided coin of the problem statement, we just talked about getting data out. in order to get data out, typically you got to start with data in. So it's really cool if we can say we can get data out really quickly, but that doesn't help any of you if you don't have a graph to begin with. So the cold start problem is usually the biggest headache for anyone in the data science ecosystem, whether you're building a new machine learning model or just trying to build a graph. So Neo4j's traditionally had some really good tools to help solve this efficiently. And we started developing some really cool tools that are more inclined to like enforce best practices and drive this concept of graph data modeling as part of your ingestion design. So things like Neo4j Data Importer. If you haven't seen it, it's really great. It combines the Neo4j arrows, no pun intended, kind of draw the graph schema as you envision it, map your data sources to it, and it will generate the cipher, use a JavaScript driver in your browser, and actually build the graph for you in the back end. And it does all the things around batching, concurrency, creating indexes, etc. But typically, if we think back to this ecosystem from one of the previous slides, we're talking about data scientists, data engineers, people moving into the traditionally called the big data space. They're no longer just a couple CSV files on a laptop. They could be thousands of CSV files on a large object store, HDFS or something like that. Or maybe they're not CSV at all. Maybe they're Parquet or Avro or some other format. And from what I've seen as data scientists, we typically have very little access to the systems we use because we're not IT. We have oftentimes no file system access to the Neo4j server. We have very large data sets, like I mentioned, that are too large for a drag and drop type of experience, especially with data importer. And then lastly, experimentation is all about iteration. You don't do one experiment and walk away satisfied. You typically repeat them. You typically iterate, change, tweak. It's science as well as an art in a way. And so you need that kind of repeatability to be as fast as possible. As data engineers, we have some of the similar problems, but we still really focus on that core integration friction point of, okay, we've got this massive data lake we've built up over the years before they were even called data lakes. We've got the remnants of the last 15 years of investing in big data platforms and just collecting, quote, the digital exhaust. The data scientists want to pull some data out. I need to prepare it, clean it, stage it, and get it into the graph. And chances are, as a data engineer who's walking in the door into this conversation, you may or may not have experience with Neo4j yet. You might not know Cypher. You might not be an expert on batch or bulk loading of data through Cypher and things like the drivers. So this is really a multifaceted problem. Everything from just complex tooling, needs around large scale, and ultimately performance. And the nice thing is with the arrow approach, just to kind of show you some back of the napkin type experimentation we did to compare and contrast. Neo4j admin import, for those who are aware, this is our existing offline scalable database builder. So it can take source data in the form of nodes and edges as CSV files and build a database in an offline fashion, which means it can do it at scale extremely fast and it can do it in parallel as well. So utilizing numerous CPU cores on the box and multiple readers and writers of the file system concurrently. So taking a large graph, so graph 500 scale 31, so it's sort of I believe it's like a randomly generated graph. Net result, it's a billion nodes, 17 billion relationships. The important thing here is we also didn't use any properties. So this is like the most bare bones graph you're going to get. You get one or numerous CSV files of just node IDs. Think of the range of numbers, integers from 1 to 1 billion, and then 17 billion relationships. So let's just say we randomly generate 17 billion pairs of those node IDs. It takes about 8 hours and change on one of the servers in question. We were running this on pretty large box, and at a rate of about a little over 500,000 quote objects per second. So that's including node loading and relationship loading. With the Apache Arrow-based approach, not only are we able to change the loading kind of design. So in this case, instead of staging CSV files on the file system like we had to do in the above experiment, we were able to stage the data in BigQuery. So something closer to what the source data might actually look like. People might have a data set already in BigQuery, or they know how to use BigQuery in order to massage or transform the data into a new data set. Using PyArrow as the kind of glue, piecing these things together, we were able to build a database that's not only larger, so 10 billion nodes, a factor of 10 increase here, 2 to 3x the relationships, as well as including node and relationship properties in under the time it took us to build, this, a smaller graph locally from CSV files. And this was going directly from BigQuery to Neo4j. So like this is really probably the real killer feature here in terms of using this approach. It's not only were we able to get higher throughput in getting data in and building a net new graph for our data scientists in this case, we were able to do it without having to commit unnatural acts of converting source data into CSV, copying them over the network to the server, having access to the file system, etc. So if this hopefully has convinced you that you should stick around for the rest of this session, great. Let's talk a little bit about what Apache Arrow is, and this will help us talk a little bit about how it differs from things like Neo4j Bolt, and hopefully kind of dispel some of the confusion around Arrow versus Bolt, things like that for folks who have seen some of the experiments in the past. So the first thing is really, it's not related to arrows.app. So arrows.app is our free graph modeling tool created by some of our engineers. It's a fantastic GUI-based, browser-based way to draw and experiment with designing a label property graph. Apache Arrow, and I'll try to keep saying Apache Arrow to disambiguate it, is actually a project from started about 5 years ago or so. I believe it spun out of some work that was part of, I think it was Apache Drill. I can't quite remember, but it wasn't just a complete start from scratch type thing. It was something that was carved out of a larger big data project under the Apache umbrella. At the core, Arrow is really, or Apache Arrow rather, is a protocol. And it's a protocol all around representing vectorized data. And so we'll talk a little bit about what that means, and I'll show you some examples. The important takeaway is that while it's implemented in C++ at the core, the Arrow or Apache Arrow libraries are available with wrappers for Java, Python, .NET, Go, JavaScript. You'll notice I bolded those because conveniently, those are all the languages that we ship official drivers for. But there's also wrappers for Ruby, Rust, MATLAB, R, you name it. Some folks are contributing more as we go. So the nice thing about the Apache Arrow project is really its design objectives to be focused first and foremost on this efficient representation of data, as well as the efficient access and manipulation of that data. So trying to minimize things around memory copying, minimize complexity and random access of the data if possible. So given a vector, can I immediately seek to a particular part in that vector? And then when it comes to particular operations, making it more friendly for modern CPUs to be able to do vectorized instructions. So to take a look under the covers, so this is kind of just the details of how Apache Arrow works. This is from the Apache Arrow website and documentation around the protocol. Let's take a simple 32-bit integer array or vector, if you will. And let's say this is also nullable. So we've got some sparsity here in our vector or array. So it could be as simple as, okay, we've got 1, null, 2, 4, and 8. In the Apache Arrow world, this is going to be represented as multiple buffers. These buffers are what are put in memory or put on disk. And in this case, the important thing is that the single vector or array is actually represented by 2 different buffers in this case. So one is called the validity buffer. It's really a bitmap saying these are the parts of our buffer that are validly populated with data. And then there's the value buffer. So you'll notice the value buffer now has these chunks of 4 bytes each, because this is a schema focused type view of our data. We said when we created this vector, we were considering it 32-bit integer. So 32 bits is 4 bytes. So we've got these chunks of 4 bytes each represented in this value buffer. So bytes 4 through 7, right now, you'll see it says unspecified. This is that null, this is that gap in there. And then you'll notice bytes 20 to 63 is also unspecified. So there's this idea of some padding at the end. So you can say, okay, let's allocate, in this case, 64 bytes to hold our vector. We've only populated a couple values, but now we can treat this as one big contiguous piece of memory. We can move these two buffers around separately if needed, write them out to disk, shuffle them around, and we still have all we need in order to access a single element within our array. When we start looking at how Bolt works, Bolt, if you aren't familiar with how the protocol works under the covers, is really a combination of the messaging protocol between our drivers and Neo4j, as well as the serialization kind of protocol as well. And so when you talk to Neo4j, it's sort of like any relational database where you get back rows. And so in this case, we're dealing with horizontal data, not kind of the columnar vectorized data. And so a record can be a series of different data values or types. If you look at the two examples here, one is a record of 3 strings. Each string has numeric values in it, but they're actually strings. The second one is more complex. The first value is a point, which contains multiple values. Technically, it's a map or an object. The second value is a string, etc. And so you'll notice this is more of that horizontal view of the data versus in Apache Arrow, we're dealing with a single column at a time. If you've worked with a columnar database before, you might be kind of familiar with these types of patterns. If you've used the Parquet format, Apache Parquet, it's a vectorized format versus Avro, so it's more storing data like with Apache Arrow. But that doesn't mean that you can't do complex things like you can with Bolt. So one of the questions that comes up a lot is, okay, Apache Arrow, I need to know the schema for my vectors. You just showed me a scalar. I get it for data science purposes, like a feature vector. But if I want a vector of vectors or I want complex objects, is it supported? And the answer is yes. You basically weave these things together into these nested buffers. So if we take a look at like an array of arrays or a list of lists, depending on what vocabulary you want to use, you'll notice what changes here is that we really end up with a little bit more complexity in the terms of an extra buffer from Apache Arrow. So we still have our validity buffer and our values buffer, but now we've got this offsets buffer as well. So the way it's designed is if you're saying, okay, I'm going to have a list of lists of 8-byte or 8-bit integers in this case, that's what we're constraining this to. Maybe it's sparse, and so we have some nullability. Maybe we have some lists that are explicitly empty, like this last item. All you need is 3 buffers in length. You've still got the validity buffer to know where items are populated. An offsets buffer basically allows you to view the values array and say, okay, for this value, how far do I need to seek? Because maybe I need to seek into the first element of the first array within our vector. Ultimately, it's able to handle this type of complexity. So that's the real peek behind the scenes, kind of give a framing of how it differs and how it's able to handle basically any sort of structure you want, as long as you can define the schema. The cool thing about Apache Arrow is you probably already use it today. So if you're using Pandas, if you're using Databricks or Apache Cassandra, or even BigQuery, and potentially things like MATLAB, under the covers, a lot of platforms have adopted Apache Arrow as either the efficient way to represent data in memory and to read and write it to disk, or they're using it for data transfer over the wire as a serialization and deserialization format. The cool thing is you're probably getting these benefits and not even realizing it. So if you look at the Dremio website, they're one of the kind of corporate, I don't know if they're officially a corporate sponsor, but they're a good handful of Dremio engineers that contribute to the Apache Arrow project. they kind of promoted some improvements that shifting some of these platforms over to use Apache Arrow, like what they saw in terms of performance gains. So, just reading from Parquet into an Arrow-based format in memory, they saw speed up. Using pandas, they can get much more throughput in terms of reading data. And supposedly IBM measured a 53x speed up in data processing. Not sure what that means, but the proof is in the pudding, really. We just talked about the serialization format, so the way the data is represented, but the way that we take advantage of it with Neo4j is actually as the basis for a RPC framework and for streaming data. So the Apache Arrow Flight kind of sub-project, if you will, is really a additional optional capability as part of the Apache Arrow project that's all designed around building streaming services. And so it's great for if you need to stand up a new service within your existing application and you want to be able to read and write data as a stream with multiple readers or multiple writers. It is basically a toolkit. So, you have to design the application around it, do all the work, but it comes batteries included with things like gRPC, which includes the transport layer of HTTP2 and some other serialization stuff. Ultimately, it's kind of like GraphQL is to Neo4j. It doesn't, replace anything. It just enhances it and gives you more of a rapid development environment to build. And this is what we've incorporated directly into the product. And so lastly, where can you find it and what are some examples before we jump into the hands-on? The first one, and probably the most important, is actually in the Neo4j official Graph Data Science Python client. So if you're already doing a pip install Graph Data Science, you already have some of the fundamental capabilities on the client side to take advantage of Apache Arrow. There is a Neo4j_Arrow Python module, not to be confused with Neo4j-Arrow. It's still kind of a work in progress. It's available under the Neo4j-Field GitHub project. And it was originally created for the Graph Connect 2022 keynote demo. And it's something that I've been working on kind of improving. We'll be using it in exercise 3. And what it is basically a wrapper around PyArrow, which is the official Python Apache Arrow module itself. And it's designed to encapsulate any of the kind of unique Neo4j-isms that we've built into our Arrow Flight service. So instead of having to construct raw Apache Arrow messages and send them back and forth, it takes care of some of that for you. There's also a Google Dataflow Flex template that's a work in progress. It's also hosted under the Neo4j Field project. So if you're somebody who works within GCP and you take advantage of Apache Beam and Google Dataflow, most of it should be portable to any Apache Beam environment, but this project in particular is designed around building the Dataflow Flex template. It uses Neo4j Arrow, the module, and has some example pipelines that you can use in Apache Beam for loading data, let's say from Google Cloud in the form of Parquet files and Google Cloud Storage or tables in BigQuery. And then lastly, one of the examples here is still a work in progress, but it's a plugin for Apache Hop. So if you attended Matt Castor's session, I believe it was yesterday, previous to this one, it's a fork of Hop that has a plugin for reading and writing Arrow format. So the idea and the initial intent around this is to give somebody using Apache Hop the tooling to interoperate with the Neo4j Arrow capabilities. So if you have, let's say you pull back node vectors or node embedding vectors rather from the graph at scale, and you want to decode those and pivot those into row-based data in your pipeline, you can do that, as well as the other way around. So maybe you have some input data in some rows. You want to do some data cleaning manipulation. You can then pivot those into vectors and use the Apache Arrow Flight service in Neo4j to build a graph. So some concrete examples of this stuff. Probably the most interesting one is the Graph Connect demo. It's available on YouTube from our Graph Connect keynote. You can watch the video of Alicia Frame demoing it in about 5 to 10 minutes. And it really is just kind of what I consider 3 easy pieces. The data is in BigQuery. There's a Jupyter Labs Python kernel in the middle, and then Neo4j on the right-hand side. And the reason why we did this with BigQuery is that natively BigQuery can give you Apache Arrow vectors as data. And you can just basically pump them through from end to end into Neo4j now. And so if you have a BigQuery table and you've already pre-formatted it into something that represents a node or a relationship, you can just say, okay, BigQuery, give me this table, chunk it into these substreams, and as you read from them, you're going to get back native Apache Arrow buffers. And what this allows you to do is very easily take something like a small BigQuery wrapper. The example code's linked down below, or I think accessible via the QR code, last I checked. And since you can parallelize reading from BigQuery, you can also parallelize writing to Neo4j. So that, I can't remember how large, it was like 240 million nodes and like 1-point-something billion relationships. We were able to read from BigQuery and write it into Neo4j into the in-memory projection in the Graph Data Science platform in, was it sub 5 minutes? It was live during the keynote, so I recommend going and checking that out. I do get questions around, can I use this in Apache Spark? The answer is yes. There's some design considerations in going from row data to vectorized data, but it's not too complex. So if you're using some of the capabilities in Spark, you basically transform the data like you would normally. You could read from a source system, like in this case, BigQuery. I have some sample code here linked from this slide that shows how to basically take rows, batch them up, and translate them into arrow vectors. But once you do that, you can use all the tooling you're going to learn today in order to insert it into Neo4j. And lastly, I think Apache Beam is probably one of the more powerful ways to integrate with Apache Arrow, assuming you have a large amount of data and the orchestration time isn't something you worry about, because Apache Beam is not instantaneous by any means to get a job up and running. But for instance, we were able to load with 68 Beam workers a pretty massive data set, multiple terabytes of data in under 4 hours. And this was early on, when I think with a pre-release version of our Apache Arrow support. What does that look like? If you're familiar with Apache Beam, this is the Python-based SDK. In this case, the pipeline was super simple. It was read Parquet files from the source, send them to Neo4j. So send table, this function is using the Neo4j Arrow module behind the scenes that we're going to get into. And then lastly, we're just logging some of the output of the details. So it really is just using Beam to do some massive Parquet reading and then writing to Neo4j. So let's get into it. So for those who are going to follow along either after the fact or on their own, you can definitely go grab the GitHub project that I will be linking here in the chat. Let me pull it up here. Let's break out of presenter mode for a second here. Some of this will be taken care of for you. I'll put it here for my co-host to share with folks. Wrong button, slideshow. In order to use Apache Arrow, you need a newer Graph Data Science install. So 2.1 or newer. 2.1, I believe, was released end of spring this year. So April, May timeframe, I think. All the details are in the official documentation. And ultimately, there's a single kind of, quote, power switch for turning it on. So you do need a licensed copy of Graph Data Science. In this case, the server I've stood up already has one. If you have Aura DS, it's now available out of the box, so you don't have to worry about any of these configuration options. You can just go spin up a new Aura DS instance and Arrow is available for you as an interface. And like some of our existing connectors, if you're the sysadmin who has to install this, they're just a couple properties to configure. Like I said, if you go use the repo, I've got a script to spin this up with Docker locally. I'll post a link to a trial license that's good for the next 24 hours in a moment. But you really just need to set the listen address or advertise address. Those are the core things to make match. If you're familiar with configuring anything else for our drivers or for the web interfaces, this should be pretty similar. So the nice thing is there's not much work to do to get it turned on. And then the way you can check your work, there's a stored procedure called GDS debug arrow. And so if you're the admin who's responsible for installing this or you're experimenting locally, you should be able to call the stored procedure and get back something that looks sort of like this, depending on what your host name is and what you set it to. But you should see that it's running and that it's enabled, and then that you've got certain addresses set. The server location is actually, I believe, going to be used by the Graph Data Science client. So if this is not externally resolvable by your users, so like if a data scientist is going to use a Jupyter environment and connect to the system, whatever host name or IP and port are put into these values should be resolvable and accessible from that Jupyter kernel or from their workstation, wherever it may be. Just kind of important to know. So let's get into some exercises. So I believe I've put the link to the notebooks in the chat. I will pull up. I will also copy this link to this Google Sheet that can be shared with the audience today. And so this Google Sheet has usernames and passwords. So please be kind. This is a system I stood up on my own. These are usernames for the Neo4j users. So please select any one of them that are not taken yet. Once you've taken one or assigned it to yourself, just put a little note or an X in here or something. You'll notice at the bottom here, I'm reserving the last one for myself. If you happen to take one that somebody else is using, you're just going to trample on each other. So, please be kind. Don't do anything silly. I'm trusting everyone here will be well behaved and on their best behavior. The Neo4j host is linked here. So nodes.neo4j.academy. You should be able to open this and get access to the login for the server in question. Now I have the Neo4j admin password, so I can log in and I'll give you a quick tour of what we're looking at here. Every user, when you log in, will have access to a database specific to that user. Now I did only set up 256 today, so I'm sorry if there are more people trying to access it than that. Feel free to watch along or try this afterwards. And the thing I wanted to do quickly was just put in a trial license for anyone who's doing this locally. Let me quickly add a file from my file system here to this gist. While everyone's grabbing their login and trying to pull up browser, this gives me a moment to do that. And if you can also pull up let's see. Yeah, this is the link for the notebooks. I'll show you how to access them from Colab in a minute. The notebooks, you only need that link if you are essentially going to clone or download the repo as well. Let's see. If GitHub will cooperate. There we go. This should be a trial license of GDS for folks that need to follow along locally with Docker. It should expire, I believe, tomorrow afternoon. So if you're looking at this event after the fact, reach out to us and we can, if you don't have access to an enterprise GDS license, reach out to your Neo4j contact and we can get you set up with one. So people are taking some accounts there. Very good. I will grab my password from user255. And when you log in, you should see basically not much. You should see in your little drop-down system and your little home database. Ignore this one for exercise 4 here for myself. But there shouldn't be anything in here. Now, technically, you can go ahead and create stuff in this database, but there's no need to. What we want to do now is if you've grabbed either the project locally, there's a Neo4j 4 shell script that will launch it with Docker, and also one for launching Jupyter. Ignore the Neo4j 5 one for now. I'm still working on updating this for Neo4j 5, but you just really want the notebooks in question. So before we dive in, the notebooks are organized into 2 directories, one called tasks and one called the answers. The notebooks look the same, except for the ones in the answers have all the answers. So if you're trying to do this in a learning fashion and want to do this in the way I've set it up initially, I recommend only use the notebooks here in the tasks directory. We'll be going through these. If you get stuck or you don't want to work through the exercises and you just want to click through and just kind of like read the code, the answers are basically where you want to go. But this way that if you are not able to complete all the exercises today, or you want to do it at a later date because of maybe you're not able to get connected today, the answer should be there. The way this is designed, as you'll see in a moment, is it's really kind of self-service and stepping through and kind of testing and checking your work. So let's pull up Colab now. I'll be using Colab. Obviously, feel free to use whatever works for you. In Colab, if you go to colab.research.google.com or just Google Colab, you should be able to open a new notebook from GitHub. Now, the GitHub repo is under the Neo4j field organization, and the repo itself is called nodes 2022-arrow. There's only one branch, so ignore that. But if you can get to this point, you should see the notebooks accessible down below. Now, technically, the answers are in here as well if you scroll down. The reason why I broke these things out in the subdirectories like I did was to basically game the sorting of Colab. Where before, in a previous incantation of this, when I did some internal training for some folks here at Neo4j, the answers were popping up at the top and people were accidentally loading those first. So this hopefully avoids that spoiling. But exercise 0 is basically a test of some plumbing. Technically, I forgot to update this one, but this is a good way for us to step through and get started. So I'll give everyone a moment to get to this point. But you should be able to load exercise 0 in Colab or in your local Jupyter environment. Ultimately, as long as you have internet access throughout this, you can go through these steps to do the install. This section is common in all 4 or 5 notebooks. There's a cell that has some flags around use TLS, Neo4j host, URI off, etc. This should be the area that you can tweak things in order to either point to your local instance. So if you're using Docker, this is actually going to work just out of the box for you. If you're using the hosted demo server because you signed up in the Google Sheet, you want to use nodes.neo4j.academy as the host. And then for the authorization tuple here, you use your username and password from the sheet here. You'll also want to flip this to true for use TLS. So all the notebooks should have something like this populated in exercises 1 through 4, where I think it'll say user 255. You need to just change this to your user. I believe I have the password set to like XXXX or something like that. So make sure you just update this line. But I believe the host name should be correct, pointing to our demo server, as well as use TLS, flip to true. Once you get this up and running and you toggle those settings, after you click through the little warning about this not being a notebook authored by Google, you should be able to step through and run each of the cells here. So you'll notice that really all we need for most of these exercises is the graph data science library. Technically, I include pandas and IPy widgets in the pip install line because not every Jupyter kernel has those already baked in. But the first real test of things being working from a connectivity standpoint is this third cell. You should see a GDS version come back. This should match what's installed within the Neo4j environment you're using. Now, if you're using Aura and Aura DS, I believe you have to say something like Aura_DS equal true. Otherwise, it will fail. I think it might actually give you a nicer warning these days telling you to do that. But for now, you might have to throw that in any of these graph data science constructor lines here. If you're using my server, you should see version 2222. And I believe I also bundle that plugin as well. Oh, lastly, if you're doing the self-guided or self-hosted approach, you need to create a licenses directory and put the gds.license file in there in the project. I didn't document that, sorry. So let's step through a bit here. So a couple of these are just to kind of introduce you to this graph data science client. If you've never used it before, this will be a little bit of a crash course. If you have, great, this should be pretty familiar to you. So this acts as our client to talk to Neo4j as well as to all the graph data science capabilities in the platform. So when we run gds.version, this is actually running a Cypher transaction that actually just returns the value of the gds.version function. Just like if we go in the browser and we said return gds.version, let me zoom in a little bit here, you should get the same result. So this is this nice little wrapper. So you don't need to learn about transaction management and sessions and all that stuff that an application developer would need to know to use our drivers. This takes care of all that for you. One of the kind of best practices in these classes I've run is to use the debug sysinfo capability within GDS to double check, are all the settings turned on right? So here you should see that the version matches should be the same thing we just saw. For Arrow or Apache Arrow to work, we need GDS edition to say licensed. Version, the Neo4j version, in this case, we're using the latest 4.4. All the other settings don't really matter. But if you're trying to understand what somebody's configured for you, let's say you're just a consumer of Neo4j and somebody else stood this up, it being the server, installed everything for you, this is a way to kind of peek and say, okay, well, what's the memory I'm being given? In this case, we've got a heap size that's pretty large. Actually, this isn't even showing the actual JVM heap, but it's in this data frame. Lastly, you'll notice that we pulled back this info object through the GDS client, and you'll see this rendered nicely in Colab, and that's because the GDS client is all designed around data frames, pandas data frames to be specific. And so it's giving us back data in the form of the data frame, typically by default. Let's see if I mouse over it in Colab, it's saying the data type is actually data frame with a shape of 93 by 2, which is really cool. So if you've been using our Python client and not the Graph Data Science client and doing conversions to and from data frames, I really recommend you just kind of switch to this workload or workflow rather, and using Graph Data Science client. The way you set the target database, and this should be updated in all of the notebooks from exercise 1 and on, is just the set database method on the GDS client. In this case, everyone does not have access to the Neo4j database. They have access to their own database, which is based off of their username. So actually, I want to change it in this one and run it, and you shouldn't get anything back. But if you can get that far, then all the connectivity is sorted out, which is great. And so now we'll talk a little bit about the those use cases of ingress and egress with the rest of the time today. And so when we talk about ingress, the most common thing that people ask about is, I can get my data into a data frame. How do I get it into a graph? And so this is where this Graph Data Science client plus Apache Arrow is really going to pay off. Technically, some of this stuff you can do without the Apache Arrow support. The performance will suffer. So you can do it for small experimentation, like at this scale with this instance data we have here. But if you're going to want to do it at scale, you need to make sure the arrow plumbing is there and activated. So let's say we want to create a very simple graph. We're going to just create this, bare bones graph. We're going to create a data frame that represents our nodes. We're going to use pandas to just instantiate a data frame from a dictionary. You'll notice that there's a particular schema I'm giving it here. Everything I'm doing in these notebooks, consider it sort of reinforcing a best practice or default value, that if you follow this approach with certain things like the naming of node ID and labels, you'll save yourself having to do extra configuration to deviate from the norm. So everything I'm doing here is really prescriptive. I'm not just arbitrarily choosing this dictionary entry called node ID. This is what will represent the unique identifier for each of our nodes. So we effectively have this nodes table. So, this could come from CSV, it could come from Parquet, it could come from Avro, it could come from whatever. Postgres, Redshift, who knows? Ultimately, we get it into a data frame, and that data frame has particular fields and members to it. So rendering it in Colab should look pretty obvious. We've got this column called node ID. You'll notice our node ID jumps up to I don't know what this is, 60 million. So we've got this, in theory, this very sparse node ID space. Each one of the nodes has a label. Now, technically, we can add list of lists in here, but all of these are strings, and these will represent the labels we put on our nodes in our graph. So if you're not familiar with the label property graph concept, nodes can have 0 or many labels that basically give them a kind of like a semantic designator. One way to look at it is it's the table name you would use in a relational system. Often you want this to be a way to sort your nodes into sets. And those sets could intersect because we can stack labels, but you ultimately want to use labels to slice and dice and partition the graph into sets of nodes of different types. Lastly, anything else I throw in here can become a node property. And so we're going to be generating a graph projection, as it's called. And we do have to obey the constraints of the Graph Data Science platform with a Neo4j if we're going to take this approach. That means that we can only use numeric data at the moment. We don't yet support categorical variables, and I don't think we're supporting strings yet. But that does mean we can use scalars of integers or floats, as well as arrays of integers or floats. So here we've got a list of scalars of integers and a list of floating point values. And when you pivot this into the data frame format, you can see that it's, each one of these nodes is going to have a single property called prop1, a single property called, or another property called other property, and then they're each going to have their independent values. For relationships, it's very similar. It's effectively an edge table. If you're not familiar with how to kind of design this, we really need a mapping. I guess you can consider it a function as well. It's a mapping from a source node ID to a target node ID. That's literally what we're going to call these two fields. So at minimum, we really need those two things to represent a relationship. So we've got a pretty boring graph. We're going to connect 0 to 1, 1 to 2, 2 to 3, and then the 60 million item to itself. So we effectively, if you can kind of just mentally visualize this, it should be pretty easy given this simplistic scale. We've got these two isolated graph components, a single node with a self-reference to itself, and then these three members with this little triangular structure in a way, or actually not even a triangle because it doesn't connect back to 0. We give the relationship type using relationship type field. So just like with labels, it's a string. So if I want to change the types here, you can just change the string value here. They can be mixed if you want. And like with the nodes, any other values can become properties. So we can then create a thing called weight, for instance. So we're going to have a weighted graph. In this case, we're going to put a weight of 42 on this self-reference here on node 60 million. So pretty basic. So that might be a little bit trivial for some folks. So the important part here is now taking these two things, nodes and relationships, and building the graph. So we've got them as two separate data frames. Let's put them in Neo4j. The easiest way to do that is, once again, through the graph data science client and calling gds.alpha.graph.construct. So it sounds like a lot of words, but it's kind of a nice hierarchical namespace here. And you really just need three things. You need the name of the resulting graph, or in this case, the graph projection rather. So let's call it my-graph- whatever the time is. We create graph projections within databases. And so you will be creating a projection in your own home database that nobody else can see, except for me. So it doesn't really matter what the graph name is here, as long as it doesn't collide with an existing graph that you have. It could be the same name as somebody else's. And then we give it either one or many nodes. So in this case, we can give it a single data frame or a list of data frames, and then another single data frame or list of data frames for the relationships. And when you run this, behind the scenes, all of the Apache Arrow integration is taking place for you. So if you had access to the server, what you're going to see is something like down below. What you should get back on the client side is something around this 10 kilobyte memory usage, which is just checking that, yes, the graph is loaded in memory. You can then go over to Neo4j browser and do something like call gds.graph.list, and then you should see your graph created here on the server in memory. Memory usage should be the same value that you got back from the clients. You'll see the node count, relationship count, etc., just like you would if you were using all the stored procedures. On the server side, and so if you're an admin or you're debugging or you're doing this all locally and you're kind of curious what's going on, you'll see that there's a particular messaging flow that occurs in the logs. So there's a create graph event that occurs. We stream the nodes. We say the node load is done. We stream the relationships, say the relationship load is done. Voila, we have a graph. So if you're trying to debug what's going on for some reason, you should see this sequence. We're going to revisit this when we get into the exercise 3 under the covers. But for now, if it's working, you should just smile and we can move on. Lastly, a quick refresher. If you're not familiar with the graph data science client, the way you run an algorithm, if you're not familiar with Neo4j's data science capabilities in general, you would use stored procedures from Cypher, like call gds.wcc.stream, give it a graph name. So in this case, I can run it on this graph. And we're running weakly connected components, otherwise known as union find, against this in-memory graph projection. And the results come back as, in this case, a kind of list of rows, node ID, component ID. So we can see we've got two components here in our little graph, which is what you should have kind of conceptually visualized if you're following along. The way you do this with the graph data science client, you take that same namespace approach, but you're just calling it sort of like a method in Python. So as long as your GDS client is still connected, you'll notice we give it a reference to the graph object, which is created by our projection up above. So as long as you got G, or whatever you called it, floating around here, you can just pass it into one of the algorithms. You can pass in arbitrary parameters. And then these will get turned into the arguments that get passed into the stored procedure for you. Really nice. Lastly, the important thing is, your mother doesn't work here, I don't think. Maybe she does, I don't know. But if you want to drop the graph to free up that memory, maybe you're done whatever experiment you're doing, you can just call the drop method. You should see details on what was dropped. And now if you go back into something like browser, say, okay, list my graphs, you shouldn't see anything. Voila. So you'll notice that at no point did we actually touch anything named Apache Arrow, which is really cool. This workflow should actually work without Apache Arrow, technically. It just will end up using Bolt under the covers here, which at this scale, you'll really probably never notice the difference. We use tools around like pandas, for instance. We weren't using anything really Neo4j specific. So, anybody who's learned how to manipulate data frames, load them from source data, this should be pretty accessible to them. That was the bare bones. So let's actually get into something more interesting here. So if you go back into that GitHub repo, exercise 1 is all about loading Parquet files. Now, these Parquet files could be anywhere, depending on where you're running your notebook, what platforms you're using. They could be in S3, they could be in GCS, they could be in Azure Blob Storage. It's a common request I've seen where folks have Parquet files. They're able to build them or export them or something, and they say, hey, I want to build this graph from Parquet. How do I do it? So I technically included the files in the repo. These are pretty small files for our purposes. We'll be using 4 different files that represent a couple different pieces of a graph. These are designed as a subset of data from one of our end-to-end fraud demos that Zach Blumenfeld has published. So if you're interested in sort of the backing kind of story around this, feel free to Google. I usually just say Google Zach, Z-A-C-H, and Neo4j. And you'll find his blog posts, exploring fraud detection, for instance, with Neo4j. And so I borrowed those files, turned them into Parquet, and simplified them for our use case here. But what they represent are, was it fraud detection? No, it was the entity resolution demo, sorry. But this data set represents fictitious users accessing a website from different IP addresses. And it is a fraud detection, scratch that. Users of a peer-to-peer money network access the network from different devices with IP addresses, and users can refer each other. So pretty simple. There's, in this case, in exercise 1, we're going to try to construct this monopartite graph, which in Cypher looks like this. User referred another user. So for instance, I don't know, Venmo or PayPal, I get a referral bonus from them to sign up my friends. I give them a code, they sign up. There's now a relationship created where I referred them into the network. Simple structure. So we've got 2 input files. We've got a user file that represents our user nodes and a referred file that represents all those referred relationships. Pretty simple, but pretty useful pattern to start from. For those working locally, they're included in the input directory. For those not locally, I've got them hosted in a public Google Cloud Storage bucket. Technically, you should probably even be able to generate the raw URL from GitHub if for some reason you can't access anything under this domain. I know some corporate intranets might block it. But all our files are accessible there under the same file name. So we've got a new notebook. We'll just go step through these initial steps here to get things loaded. You'll notice that there is this new module we're pulling in from GitHub called Checker, and I'll explain what that is in a moment here. Ultimately, it's going to be what checks your work as you go about this. And we'll go through the first one together. Unfortunately, I don't think pip can cache it because it's pulling it down from GitHub. So it's usually a little bit slower to pip install. You'll notice we're just importing pandas again, in this case, the checker and our graph data science client like before. And then this is what you should need to tweak. Just change the username to your username and then password to whatever your password may be. So here's the first task. This is where you start doing a little bit of work on your own. Since this is a workshop and you've got like 45 minutes left, we're going to kind of work through this out loud together. Wherever we end up, I might skip ahead to some exercises if needed, but this is where you can start to do your work on your own. I'll keep the server up for at least another 24 hours or so. So feel free to complete this at your leisure today. So first task is to create your graph data science client and set the database. So this task, oh, actually, this is the answers notebook. I might have forgotten to scrub them. I think I forgot to scrub all the answers from all these notebooks as I last updated them. Okay. This might be a little bit easier than I thought. Cool. But let's say we're starting with this approach. Each one of the tasks is going to have some sort of output we want to generate. In this case, first step is to get connected. We need a client that's set up and running. So I want you to generate a instantiated client that can authenticate and is referred to by the variable name GDS. So how would we go about that? And I'm going to update those other notebooks in a second behind the scenes while people work on this one or step through it. We create a graph data science client. We give it a URI, which you can use, the cheat sheet up above here, these variables. We authorize it and we set the database. In this case, you can use Neo4j _auth and the first value of that tuple to target your home directory. So let's say you do this successfully. Click play. And now to check your work, you'll notice this cell, I ask you nicely, don't change the cell. The checker, you tell it which exercise and task you're in, and then they should all be pre-populated with what they're going to check. So when you run it, if you ran it, or if you did your work successfully and correctly, it's going to do some validation behind the scenes, inspecting these objects you pass in, and you should get a little celebratory, congratulations type message. If for some reason, let's say we set GDS to something totally bogus, and I rerun it, you'll get a little warning light and a failure. And depending on the type of task and how much work I put into the checker, you might get a little helpful message about what was wrong. So in this case, we're failing a type check that, I was expecting you to instantiate a graph data science client. You gave me something else. So we'll work through this, let's say, independently for now. So go through these tasks. I know technically these have all of the answers. Meanwhile, I will quickly update the next notebook to solve that problem, because that is funny that I, in my haste, forgot to delete the answers from the exercise ones. That's pretty funny. It's not Monday either, is it? No, it's Wednesday. So yeah, you'll have the answers here. So step through them, understand what's going on. The important part here is we're using pandas to read the Parquet files because it can reach out to a web server and pull them in and give you a data frame back. And if you remember from exercise 0, that's all you need. You just need the data frame in the right format, and away you go. So I will quickly update this thing while people tinker. This will just take me a second here. And this is fine anyway, because some of these initial exercise steps can be a little challenging for folks if they haven't used pandas before or haven't loaded Parquet files, etc. Let's see. The next exercise does require understanding a little bit about some of the graph algorithms and how to call them, but we'll work through those out loud once I get this thing up to date here. This is how you know I'm doing this live and that I'm not a recording, because why would we publish this if it was just a recording? Okay. Lastly, okay, that's good. So I'll keep those the same. I'll clean this one up. Perfect. Let me push this. Excellent. Now, I'm going to step through this live so we can all see the output if people can't on their own. Double check that my GDS object is what I want. So we read the Parquet files. Let's take a look at what it looks like as well. So pandas can read directly from a URI. In some environments, you might even be able to read from Google Cloud or S3 or Azure Blob, depending on where you're running this and what stuff is installed. Our users table looks pretty simple. We got a node ID, labels field, and we got this extra property. We check our results here. It's happy. Perfect. So now to read the relationships, we can also use the pandas read Parquet method again. Make sure referred is good. Perfect. So our edge table, like we were doing with that data frame earlier, source ID, target node ID, relationship type. You know, this is just bigger than the previous data frame that we constructed by hand. Now, once again, to project the graph, we just take those nodes and relationships and we call alpha graph construct and give it a name. So exercise 1, that's going to be our individual unique names. We'll construct the graph and refer to it as G. If we check our results here, we're good. We've got a graph. You should have a graph with 33,000 nodes, 1,800 relationships with node labels of user and relationship types of referred. Now, if that was successful, we can now run an algorithm directly against this graph that was created from those Parquet files using the Graph Data Science client. So we'll call wcc.stream, store the results as a data frame called WCC. Now, before I do this next step, let's just take a look at what that looks like. So the task here is to find the number of components that we generated. So how many distinct graph components can we partition this graph into? So we run WCC, we can look at the output. I'll run it again because I don't feel like creating another cell here. And what you're going to get back, if you're not familiar with it, is the node ID and its mapping component ID. So here's where, if you know pandas, you've got the raw data. If you know Python and pandas, you can manipulate this and figure out the unique values pretty easily. I know this is one way to do it. I think someone told me once upon a time there's a separate one called nUnique, and it'll basically give me the number of unique values in this data frame from the component ID column. And now if we run our checker, ta-da, we found 31,909 components. So this is a nice example workflow of using Python, load the raw data, get in a Neo4j in a projected graph, run an algorithm, pull the data back into your Python environment, and then do some secondary analysis on it. So using the tools at what they're really good to do and what they're built for. So Neo4j built for graph analytics, pandas or whatever platform we're in, it could be PySpark, doing just simple, large scale arithmetic of, either find me all the unique values or find me the average of all these values, that type of scalable mathematics that you can use just the Python environment for naturally. So in this case, we're just saying, okay, given this data frame, just find the number of unique values. I'm not writing a cipher statement to do it. Well, I could, whatever. It's really up to you as to where you want to have that compute exist. Just use whatever's natural. So if you want to get really fancy, and this is one of the reasons why I like things like pandas. Let's say we're trying to find the top 10 largest components. You can do this in Cypher for sure. If you're trying to do it natively from pandas or Python, if you know what you're doing, you can string together a couple operations on the data frame, which is really cool. Now, if we check our results, we should see our top 10 largest graph components. So these are our largest communities based off of the weekly connected components output. Communities 4882, 2410, and 6907, and 4978 should all be of a count of 7 members. We should all get the same results here because WCC is deterministic. There's nothing random or stochastic in it at all. So all this stuff should check out on your run through. So now let's pivot over to exercise 2. Now, technically, if I updated the repo fast enough behind the scenes, we should have, perfect. We don't have all the answers in there. Great. So here we're going to work with a slightly different graph. We're going to use a bipartite graph. So we're going to look at users and their IP addresses. So in the cipher notation, we've got this user has IP type construct. So every device I've used when I connect to the network, an IP address gets logged in the graph, and then I get a relationship connecting myself, my record, to that IP via this has IP relationship. Pretty simple. So just like before, pip install, get the import set up. While that's running, I will double check. I got my password copied. We're going to use the same imports as before. It always takes forever for this very tiny little checker module to install. There we go. Import. That's updated. And now, since I'm no longer trying to teach you how to read Parquet, we're going to give you the cheat sheet here. If you're running locally, this is incorrect now. Ignore the comment. You can either use the web to get the data, or the local files. Just update the paths appropriately. But here we've got our 3 data frames. Let's take a look at what they look like. We've got our IPs. So this is all anonymized. So it's just a node ID that represents a unique IP address, has a label IP. Users we saw previously, node ID and labels. And then lastly, this should look familiar to you now. Our relationship data frame is source node ID, target node ID. In this case, the source node is a user, and the target node is an IP. The relationship type has IP in here. All pretty simple. Create our GDS client. So we use our Bolt URI, our authorization tuple, set our home database. And then lastly, if we want to construct a graph, we use GDS alpha graph construct, give it a unique name. And now you'll notice we're loading 2 different types of nodes. So we have 2 different data frames. These data frames, IPs and users, technically have different schema to them. So they have similar fields in node ID and labels. Those are those required fields. But then users have an extra property called fraud money transfer that doesn't exist in the IP's data frame. So if you have data that has kind of different properties, it's best to break them out into individual data frames. You can just pass in a list to the construct method call here. And voila, on the server side, we should now have exercise 2 loaded. And now we can start generating some features. So in exercise 1, we focused more on data ingress. We did a little bit of egress in terms of getting out weakly connected component scores, but that's not too exciting usually. I mean, it's a lot of scalars, but that's, scalars are scalable in a way. But now let's go through an exercise of generating some graph features, specifically node embeddings, and pulling those out at scale. So this is an example where the features we're going to generate are going to be larger in terms of data size or volume than the source graph was initially. So our initial data frame, these data frames aren't that big. Yes, we've got, 1.5 million rows here, but these are all integers. This is a relationship type that could be my vocabulary is drawing a blank now. One of those variables that has a fixed value. I've lost my ability to speak. Categorical, a categorical value here. You can compress this down and make it pretty efficient. Even if you look at the the size in memory, I mean, we're estimating 20 megabytes, which, you know, that's probably with a little bit of excess in there for some overhead. Not a lot of data. So first, what we want to do is build a monopartite graph, and I'm going to walk people through this step because this might not be something people are familiar with. So we want to do some node similarity first. So we've got our graph already referenced as G. So remember to call a particular GDS stored procedure or algorithm. We use the graph data science client. Now in this case, sometimes the type ahead will work in your environment. Sometimes it won't. But you can typically follow the type ahead you'd get in browser and the namespace here. So we want node similarity mutate. Now we want to say we're going to mutate this graph. And for the config, we're doing a mutation. So we want mutate property. I think you can either use snake case or camel case. I think we changed them around for you, but let's double check. We want to call this, well, actually mutate relationship type similar by IP, mutate property. And I'm going to see if I can mix these just out of curiosity. We'll do this live. Okay, so this is a good example of getting the error message back and how to interpret it. So oftentimes you'll put in something that doesn't match what's expected from the data science platform. And usually if you look at the message down below, there's a hint as to what's wrong. They've done a lot of work in trying to put in some helpful error messages here. So this is effectively a feature. So we're seeing that we're recommended similar properties here. So there's mutate underscore property and mutate relationship type. But there was no value specified for the mandatory configuration parameter mutate property. So what this means is we have to use camel case. So it's saying this is what I got, but I need at least this. Update that, rerun it. Technically, I make a comment here about setting concurrency. If you know what you're doing and you try to increase your concurrency beyond 4, I think, I have it locked down. You'll get an error message using one of the GDS admin features now that allow us to set defaults and limits. So every user other than the Neo4j user is limited to, I think, a concurrency of 4. So that means that when you run an algorithm that's parallelizable, at most it can use 4 threads simultaneously, which can be scheduled on 4 logical CPUs or vCPUs at a time. So this will take a little bit of time with people all running it. Node similarity is not the fastest algorithm. But what we're doing here is taking this bipartite graph, user has IP, and we're going to construct a monopartite graph of user to user. So user is similar to other user. Because when we do our node embeddings, we ultimately are going to want to embed this kind of user similarity network into a single embedding space. So then we can maybe pull that out and put it into some other platform that wants to analyze users based off of maybe their closeness in our graph by overlapping IPs, things like that. This is always the slowest one here. Let me take a peek at the server. There we go. I see it running in the back ends. Perfect. So you should see some output once the job is run. Check the result, because what we've done is we've mutated that graph projection. So if you actually go back into browser, rerun graph list, you'll see it's larger now because we've created more edges. And on the right-hand side, if you scroll over, the scheme has changed. We now have a similar by IP with a score value, which is the weighted edge. So to generate the graph embeddings, we're going to use FastRP. So this is similar to what we just did. We want to mutate our graph. So we're going to use the mutate mode of it. If you're not familiar with FastRP, it's an implementation of a node embedding algorithm. It's going to take what we target in terms of the graph. And for all those nodes is going to find a way to embed them in the same vector space. The result is a feature vector that represents its position in that space, and then you can use some basic vector math to do things like some sort of distance metric between them for similarity, or do clustering, etc. If you're a data scientist, you're probably very familiar with feature vectors. And let's do this. So we want to do GDS, FastRP, mutate G, you say mutate property. So what this does is generates a vector, and we want to call it FastRP. It's going to store a property on every node. Technically, we want to focus this on, and we're going to get a little fancy here. Let's see, we want to focus on, you can technically embed the whole graph, but what you really want to do is probably just target the nodes. I don't think I expect that. So if you're going to target with a label filter, that's great. Kudos to you. But let's do an embedding dimension of 256. So each one of our vectors is going to be dimension 256. That's going to dictate the size of our vector space. There is a required parameter for FastRP called iteration weights. If you're not familiar with what this is, I'd recommend checking the docs. This basically is a weight that gets assigned to the random walk from the algorithm. And let's see, no alien specified for mutate property. I did it again. Helpful error message gets me right on track. I don't know why it keeps popping up with this code snippets thing. You'll notice FastRP is a lot faster than node similarity. It scales quite well. Check our results. It passed. Technically, we'd probably want to target this on just the users or the nodes with the user label. But for the sake of this workbook, let's continue. So now we've generated these vectors. We've got, if we look at our graph again, it's now 660 megabytes in memory. Substantially larger than it was. We started with a 20 megabyte projection from Parquet. Now we've got this massive amount of data we've generated just from that small, like taking that network of nodes and generating this node embedding for the space. Now we want to get that data out. You technically, you can write it to Neo4j as a property. We can persist that into the graph along with the whole graph as a new database if you want, because maybe you want this as like a feature store. But typically, if we're doing something like this, we need to experiment. We need to even qualify, like, is this approach working? We might need to feed this into some other tool. So let's pull these vectors out at scale. So now remember, we are talking about how many nodes here? Like 620,000 nodes times 256 floating point numbers. That's, what is that? 619,587 times 8 bytes times 256, assuming worst case scenario. This is that 1.268 billion bytes, I think, something like that. It's we're talking about a lot of data, more than our original source data. So if we want to pull the data out using Apache Arrow, this is the best part. You'll notice we're not using Apache Arrow directly. We're still saying, okay, let's grab the GDS client. As part of the graph namespace, there's these streaming capabilities. We can stream different properties, node properties, relationship properties, one or many at a time. In this case, we only care about a single property in our graph, and that property is called FastRP. Now, I keep this time thingy here, can't remember what they're called. Going to give you an understanding of the speed at which this can run. Now, technically, everyone might be doing this simultaneously against the server, and depending on how far away you are from US Central 1, you'll get varying output. But we're pulling back all of that data all at once. And here it took 11 seconds from US Central 1 to my home in Vermont. which for those who aren't familiar with the geography, Iowa and Vermont, I don't know how many miles that is, but it's definitely multiple hours in a plane. And I can't get there directly either. But now we've got this data frame, DF. If we check our result, great. If you want to visualize it, it's going to look pretty sparse because we pretty massive embedding. You're going to see a lot of zeros. But if you were to say, grab the first value in here, how do I do that? I'm never very good with the indexing here. Is it property value? Property value. There's our series. Let's grab the first one. A lot of them are pretty sparse. The point here isn't to achieve a valid data science use case. It's to show the data flow. So either way, we've got this, maybe we don't realize our data's crap. We need to pull it out in order to do so. Now, comparatively, just as an exercise, this is what you would have to do using the Python driver to do this type of egress. You would have to know how to use the Neo4j driver, number one, create a graph database instance, or driver instance rather, open up a session, run a transaction using the stored procedure call. And in this case, we're just going to say, give me the first 50,000, but there's no real way to short circuit out that stored procedure call preemptively. So in reality, you're going to have to stream that out of the in-memory graph anyway into the Cypher runtime. Cypher's then going to have to say, okay, let's limit it to, in this case, what is it, 50,000 records. Needless to say, this is going to take a little while. So I'm going to time how long it takes to get 50,000 back. It's probably going to take a little bit. While that's running, in the interest of time, I will queue up exercise 3. Because we are starting to come up on the 20-minute remaining mark. Sometimes Colab does not like to open the repo I want to open. There we go. Okay, there we go. So it took 38 seconds for us to get our partial data frame back. Now, up above, you'll notice it took us 11 seconds in wall time to stream the data entirely back to my client. And that was the entire data set. So estimating and extrapolating out for 38 seconds for a fraction of the data set, it would probably take us, what is that, 8 minutes to pull back the data using this this approach. So it's not that you can't functionally do it in this case. It's just I hope you have 8 minutes on hand. Maybe your coffee's empty and you can walk down the hall and refill it. Versus here 11 seconds. I mean, that's mostly a network overhead. I can run this. I'm not going to be inclined to get up and walk away. I mean, that's really the killer feature here. So how does it all work under the covers? If you really are more on the data engineering side and you want to do some really cool integrations, you really need to understand how the Graph Data Science client is working. So the code is there. It's all in GitHub for the Graph Data Science client. If you go to neo4j/graph-data-science-client, I think, or just Google it, you can see how PyArrow is being used under the covers. So if you're really curious, this is really what's happening for you behind the scenes. And this corresponds to those log messages that we were seeing earlier in that first exercise 0 workbook, or notebook rather. You see there's really these 3 phases. You signal to the server you're about to create a graph. You then, assuming that graph is unique and you have permissions to do so, we can start sending nodes. When we're done sending nodes, we say we're done sending nodes, because any sort of stream could be anything to the server. Maybe for some reason you have a node property called source node or target node ID or whatever. You basically split your load into these 2 distinct separable phases. Once you're done relationship load, the in-memory graph pops out the other end. So there's a little bit of time where there might be some post-processing, That's about it. So the GDS client is doing this for you. If you want to do it yourself, the Neo4j project, or Neo4j Arrow project rather, can help you simplify this a bit. And it'll give you the ability to control those individual steps. So this is useful for if you want to parallelize this yourself. The GDS client does a little bit of parallelism, mostly in the form of just concurrency through some Python threading, but it's not going to do, the level of concurrency that something like this Graph Connect demo did, where this used multiple processing, Python multiprocessing, forking into separate processes, separate Python workers, all streaming data in parallel simultaneously. So if that's the level you want to get to, Neo4j Arrow, that's what you should be using. So if we quickly start kicking this off, you'll notice that right now it's not distributed via PyPI because it's just a kind of community field project maintained in our spare time. So it's not really part of any sort of package and release. So the code is there. You can go grab it, tweak it as you like. It's really just some helper code around the PyArrow integration with Neo4j. There's some stuff I've been working on in there that's not in this notebook around specifying a graph data model and then mapping some patterns against the source data to the model, but that's all advanced use. You'll notice we import it just like we did before, just like you would any other Python module, Neo4j Arrow. There's something called Neo4j Arrow client. Here we're also importing the PyArrow module because we're going to be using this with the Neo4j Arrow client. So this is where we start exposing direct access to some of the Arrow constructs. So I'm going to update my password here. The connection, it's not as elegant as connecting to Neo4j using Graph Data Science client. There's a lot more parameters you need. You shouldn't have to tweak this in your notebook if you've got the above cell set up. But just like with the GDS client, you create Neo4j Arrow client. You have to set which graph name or projection name you're going to be using. So this is one client per workload, effectively. So if you're going to build multiple graphs, yes, technically right now you have to build multiple clients. The clients are very lightweight. They don't necessarily connect and do anything until you actually use them. So don't worry about it. So just like before, we want to pull in our source data. So here, I apparently blanked out this exercise, which isn't an exercise at all. So let me grab this guy here, pop her in. So we'll be using the same data as before. You'll notice that in this particular case, we're going to still use pandas because the data on the web is more accessible via pandas. Get a data frame. But once you have a data frame, in order to get a PyArrow table, as it's called, you take that data frame and just pass it into this PyArrow from pandas class method. So pa.table.from_pandas and give it the data frame. Now, when we look at users in this case, you'll see it's not as beautiful as looking at a data frame. It's a totally different object and construct, but you get schema information about the table. So we can see the fields and their data types. These are being inferred from the data frame schema. So if your data frame's garbage, your table's probably going to be garbage. And then you can see a little bit about the data in each of the columns or the vectors. If you have Parquet files locally, or you're running in a certain environment where direct access through a cloud storage API is available, you can probably skip the pandas step and just use some other methods from PyArrow. I recommend PyArrow Parquet read table. If so, you can just read the Parquet files directly. So if we want to read our referred file into a table, in the interest of simplicity, I'm going to copy and paste from the previous one and make sure I update my variables here. So we read our referred table. So this is similar to exercise 2, but instead of the IP has IP, we're now looking at users referring users. So this is more like exercise 1, if I remember correctly. But now we've got PyArrow tables. So what do you do with PyArrow tables? Yeah, it looks good. it's our job now to orchestrate that ladder diagram, that flow. So here's where Neo4j Arrow is taking over and using PyArrow to talk to the Neo4j server, which is also using PyArrow through, well, not PyArrow, but Apache Arrow Flight. So some of the configuration and setup is being done for us in the Neo4j Arrow client, but you do follow that same ladder diagram. So you always have to initiate the protocol. You have to start. Simply calling start. What this does is actually sends a message to the server. If you notice, if you run start twice, you'll probably get an error message. This is a stateful process. We should get back an object that looks like this. This is actually the raw response that comes from Neo4j when you start connecting via Arrow Flight and send the RPC message to start and import. Behind the scenes, we're sending a create graph message with some arguments. In this case, the name of our graph we're going to create. There's some other parameters in here. It's all in the documentation officially. So this is a documented supported protocol. Now that we've started the import, we can do nodes and then relationships. So in order to do nodes, we just use write_nodes one or many times. So the same client can be used in parallel from multiple consumers. So if you have either Python threading going on, or you can technically create multiple clients derived from this client. I think I implemented it such that it's pickleable and you can farm this out into sub-processes and things like that. You'll notice we pass in a single PyArrow table here. You'll notice this is a table, not a data frame. And you can keep calling this with as many tables as you have. Tables themselves can have some batching derived from them because they have the ability to kind of be partitioned, split up into chunks. Typically, like if you're working with Parquet, you'll get one table per file. So if you're already doing something like with a BigQuery export into Parquet, you're probably fine just loading an individual file into an individual table instance and just sending that. The client will take care of some of the batching. But here we've sent our 33,000 nodes representing users, and this is an approximation of the amount of data transmitted. It's not perfect, but it's about 809,000 bytes. Once you're done loading your nodes, you have to tell explicitly, okay, we're done. No more data for nodes. Anything that comes in after this is going to be a relationship. So send the message to the server, and you should get back something pretty explicit like this, the name of the import that's still going on, and then some details of how many nodes it saw come in through the import. So this should, in this case, match what we see up here. Since we called it once with a single table, it should be the exact value. If we were loading multiple tables, it should be the summation of all of them. The important thing to note is that if you're doing some of this stuff, if you're the data engineer doing this by hand in a platform like Beam or Spark, you're going to need to understand the concept of the difference between a worker node and an orchestrator node, because you can only call nodes done once. So you might need a pipeline that reduces down into a singleton or something, which triggers this call being done. Or you might need to make sure in like the Spark world that this is being run from the orchestrator node or whatever it's called in Spark parlance versus from the worker nodes. It's usually pretty easy to do. So to send edges, this is pretty simple. We've got our client, which is what we call it, client. And since in Neo4j Arrow, I wrote the code and I'm lazy, if you know me, edges is shorter than relationships. So I use edges everywhere instead of relationships. And it's also the same number of characters nodes. Let's see. Dun, dun, dun. What did I do wrong here? Oh, that's right. I don't want to say edges are done. I want to write the edges. Duh. we send the edges. Now, technically, what the results should look similar to what you get when sending nodes. You get back the quantity and then the number of bytes roughly. So we're not done yet. We still have to say, now we say we're done edges. Edges done, doesn't take any arguments. Now on the server side, it knows no more data should be coming. It's safe for it to go do any post-processing and build our resulting graph. Technically, the result object you get back should just look like the summation of the relationship count, which in this case should match this tuple value. So what we would expect in our graph is something like this. For our nodes, we have users, and we've got a quantity of 33,732. For relationships or edges, we've got referred, and we got 1,870. So to validate our work, we can just use the graph data science client, connect up, get a graph, an instance to the graph, and interrogate it. So here we've got our graph in memory on the Neo4j server side. We get a reference to it using the graph data science client's graph.get. We use the name we used to create the graph, and voila, we've got the data we expect. If we take a look on the server side, I always hit Shift Enter instead of Control Enter. There we go. It's in our database, got our graph. If we scroll over to the schema, you'll see we've got our properties, relationship types, etc. So we didn't use the graph data science client to load or populate the graph here. We used the raw PyArrow capabilities, which if you look at that project, oops, Neo4j-field, Neo4j_arrow. It's really just encapsulating all of the state transfer, or the state changes in that ladder diagram for you, and constructing the appropriate PyArrow messages. So if you're familiar with Apache Arrow and PyArrow in particular, or you want to dig into it, you can take a look at this implementation. It's pretty simplistic because it's building off of a pretty well thought out scaffolding in terms of arrow flight. So there are a couple things around mapping and whatever and batching, but for instance, to write nodes, we ultimately call write batches, but we're constructing this particular message. We're saying, okay, we're going to be sending node data related to this particular import by name, so the graph name, and here we're saying it's going to be nodes. So every stream effectively gets this type of information attached to it. Same thing with nodes being done. If we look at send action here, it's just sending a JSON object to the server to do the signaling. So if you scroll back up to the ladder diagram, all of this is documented in the Neo4j docs. So if you wanted to implement it on your own or in a different language that's not in Python, it's actually not that hard to do. So lastly, with the last couple minutes remaining, this is good timing because unfortunately exercise 4 isn't something you guys can run against my server. I mean, you can run part of it, but you can't run all of it. It's not going to work right for you because I haven't given you permissions to actually properly create a database. You can create graph projections in a database, but not a net new database based on how I set up those user accounts. So everything up until now is about creating in-memory graphs that exist within the data science platform in Neo4j. That's great for if you're going to be running algorithms, mutating the data, and then either pulling it back out or serializing it to a file, or maybe persisting it into a net new database downline using GDS export. For cases where maybe you're tasked with building a new database, so you'll notice, all this time we've been creating this data, my database user 255 is completely empty. There's nothing in there. Here, if we want to create a database that you can run Cypher on and visualize with Neo4j Bloom and use browser and poke around, We can use a lot of the same steps with Neo4j Arrow from exercise 3, not exercise 2, exercise 3 rather, and just simply change the way we set up the initial connection. So we're going to do another user to IP bipartite graph. Kick these off quickly while we're talking so I can demo this. This is always the slowest part. Okay, we're going to run our imports. Now, before I connect, I'm going to change screens so you can't see my Neo4j password as I connect. There we go. Okay, so now we've got, in this case, a database name I'm going to create. In this case, this is going to be replaced with Neo4j -ex04. Create the Neo4j Arrow client the same way we did before. You know, it is a little bit, needs a little bit more thought and design. It's not product, so it's best effort. But basically reuse the database name in a couple of different locations. So instead of the projection name, use the database name. But we load our data just like before, where we want to turn these into PyArrow tables, pandas, df. So we want users, IPs, and our has IPs relationships here. I don't know how that got in there with my copy paste. There we go. Check our results here. Good. Data is loaded. Now you'll notice that here we're doing a little bit more complex stuff. So instead of just client.start, we're actually saying explicitly we're going to use a create database message, and we're going to pass in this bonus config. So this is specific to the implementation that you'll see outlined in the documentation around that ladder diagram. And you should get back a similar thing. Okay, here's the name of the import. So just like before, we do client dot send nodes, and we've got what, users and IPs. You'll see we do this. In this case, we can do it one at a time. Technically, you could do this concurrently. What was it? Send. Oh, it's write. I can never remember the name of it. Write. There we go. 33,000 users, 585,000 IPs. Check our results. Good. Now we do client.write edges. You'll see we're doing the exact same flow as we were before. As IP, give it the arrow table. I forgot to do, oh yeah, I'm getting ahead of myself. Client nodes done. So sometimes it aborts the whole process. So let's do this again. Start. We've got those. Let's write them. Perfect. Results. Good. Nodes done. Good. Client. Right. Edges has IP. Good. And now check result. Good. Client. edges done. Obviously, you usually wouldn't be doing this type of workflow in a notebook. So we can check to see if our database is online. So we're going to use gds.run cipher to run arbitrary cipher from the graph data science client. So it's going to try to call show databases and check for the database by that name. We found our database. We'll run some cipher against it. So here we're going to just say, find me user ID 33968 and the IP they have, if any, and voila. If I jump over to my admin view, we should have Neo4j EX04. Now you'll notice that some people are able to create some of the databases, but they can't bring them online. That's that permissioning issue with my setup. I didn't have time to get it all tooled up so everyone could actually create databases safely. But now we've got an actual database with IPs, users, has IP relationships, and the different properties as well that might have been trickled in there. So this is actually a holdover from some of the pandas junk, some index value, but we've got the structure we expect, IP addresses, users, and we can run any sort of cipher we want against that database. So just like before, if I say, here we go, IPs, has IP, etc. Fully functional database that you can now do anything you want against it. We can drop it, and voila, it's gone. So what you'd see behind the scenes, just to kind of wrap up, is similar messaging as you would when you're doing the graph projection import. You get the same type of put commands being logged, but instead you see a database import, and then you'll see stages related to the database creation. So these are the offline database creation steps that are actually the parallel batch importer uses behind the scenes, and ultimately you'll get the details here. So the import took 9 seconds total. That's sending those Parquet files over the wire remotely to the server and building a net new database. So to wrap up, the exercises, when you want to revisit them, they'll all be online. And ultimately, the takeaway for people who are curious as to, how would I summarize what we just went through? Ideally, you should really not care about Apache Arrow directly. You should care about what it's giving you. And ultimately, if we do our jobs right, our being Neo4j's jobs, we integrate Apache Arrow in a way that I won't be giving this talk at Nodes 2023. That it should just be baked into the product and disappear. Sort of like what you see in exercises 1 and 2, where people are able to take advantage of it for Ingress and Egress using the graph data science client, and it's entirely in the background. You should just be happy that things can scale, data can come in and out extremely fast and efficiently. And that when you start thinking in terms of billions, you have a way forward with doing large scale ingress and egress. So this is where a lot of folks reach out to the community or to Neo4j saying, I've got this massive amount of data in my source system. How do I do this effectively? I don't have the time or ability to stage all these CSV files, or I don't have the rights to the file system, or I need to be able to temporarily scale up the load just for this initial cold start issue. The Neo4j Arrow and Apache Arrow approach give you that ability to scale out your load concurrently. So that, if we think back to this super simplistic architecture diagram from the Graph Connect demo, this is temporary compute in the yellow nodes. So the Neo4j system deployed in blue could be an Aura DS, could be self-managed. You can spin up using an orchestration framework like Spark or Apache Beam or whatever, you name it, temporarily all these parallel data processors to stream the data into the graph or create a new database. And then when you're done, throw it all away. So it should fit right nicely into your existing approaches. So with that, I know we're at time.
Super. Thank you very much, Dave. Can we do one question, because it came up a couple of times
Sure.
during the chat today. So again, thank you very much for presenting this, for the demo, for the cool exercises. I hope everybody had a good time. But it came up a couple of times with the speeds differences between the CSV import you showed, as well as the arrow usage.
Yep.
And then you showed the data ingestion in the end. So I think a couple of the questions were answered by that. Can you actually ingest data by using Apache Arrow? I think that was showed. Is there a way to do this without having the graph data science library package? So I mean, if you just wanted to use Apache Arrow to speed up your data ingestion, to the data loading, importing into Neo4j, is there a way, or do you need to have GDS for this speed benefit? Or what is another alternative use for people who want to speed up their data loading?
Yeah. So currently it is a feature only of the Graph Data Science platform and or a DS as well.
Okay.
I can't speak for the roadmap, but it's currently only offered as part of that platform functionality. In the meantime, I mean, what I recommend is, so if we look at this, the numbers here on this slide with versus, the Neo4j admin import, the real speed gains come from removing all of this data conversion to and from CSV. So, well, today, if you don't have data science capabilities, you're still going to be using CSV. You might at least be able to kind of prepare some of your pipeline for doing some of the pre-formatting and pre-processing into the CSV files, and then cut over to using maybe arrow capabilities if and when you have GDS access, or we incorporate this into Neo4j5 as a feature natively. Because what you see here, and one of the common questions I get about the differences between, and the reason why I put apples and oranges as the icons here, as the saying goes, these aren't exactly like for like comparisons. The reason being is that in this test, we don't time how long it took to generate the CSV files, number one. So that's not even factored into this total time. That would probably be, adding to this time, most likely not subtracting, because that's impossible. But there's also non-trivial amount of CPU overhead associated with Neo4j having to read the CSV files as text and convert those strings into actual proper Java values and of different data types.
Yeah.
So while CSV can represent any data you can put into Neo4j today, that basically means that one of the reasons why this is 8 hours is we still have to create Java objects and Java primitives, and we're not even talking properties at this point in this run through. Versus on the arrow side, BigQuery is giving us vectors that have a schema that are already pre-packaged, don't need conversion, can be pretty much passed directly into Neo4j. While they do end up needing a little bit of unpacking into Java primitives, maybe, we no longer have to do any sort of type guessing. So we know for a fact, given this chunk of data, this in memory, this represents maybe Java longs, so we can more efficiently unpack it, whereas with CSV you can't. So if you're able to build a pipeline today that can at least get to the point of maybe converting into the CSV format, you'll notice that the format used here for the data frames for the Apache Arrow-based import, this closely resembles what you'd be doing with the CSV importer anyway. So it's kind of a good kind of preparatory step, such that if and when we do release the Apache Arrow capabilities or expand support into the parallel batch loader for something other than CSV, that you'll be pretty much prepared to do this. So, if you're staging it in Parquet or some other structured format, try to get as far as you can before dumping things into CSV for the importer is what I'd recommend.
Yeah. Okay. And I guess we try to improve this, like you said, all the way with Neo4j5. We have yet another way of at least initial load. It's not not for a running database, but for initial load.
Right.
With Neo4j, we try to get you another way of helping out with performance in that regard. So that's another point of getting that number down a little bit.
Yeah, and in 5, we've got the newer incremental support being added for the CSV-based importer. So, I mean, I anticipate, and this is just my interpretation, that the kind of the features are going to start to merge, where nothing I showed you in the exercises today show you how to do any incremental updates because it's not supported yet. So it's okay for building something from scratch, from starting from just a data set. If you want in Neo4j 5 to do a large bulk ingestion of a database and then do large updates, the CSV importer is adding capabilities to do these partial updates. So you don't have to go back, drop the database, or create a brand new one and cut over. So hopefully, in the next year, we'll start to see some convergence of feature sets. So it doesn't matter if you're using data science or not.
Cool. All right, we are a little bit quite over time now, so I think that's a good point to close it down. So again, Dave, thank you very much for showing us this, for giving us this workshop, and for all the exercises and specifically the hands-on part, guiding us through there. So I think that was super helpful and interesting. Like I said in the beginning, this will be available for you to watch on YouTube later on, so you can take your own time and revisit these exercises. We'll share the slide deck from Dave as well with you, so you can go through there. Obviously, the server won't be running in, if you watch this like in, I don't know, in 5 months or so, but you can connect to your own server. Maybe you try. Would it work with Sandbox, like theoretically?
I don't know if it's turned on in Sandbox yet, but I know it's on the roadmap for that.
It's on a roadmap. So okay. So at some point you will be able to try this on another opportunity if you don't have a GDS enabled Neo4j instance running. Other than that, the offer stands. If you want to try this out yourself, or really interested, you can ping your closest Neo4j colleague, and we can get you going somehow. And yeah, with that, I can only remind everybody again, please register for notes if you haven't done so. And yeah, have a good rest of your week. See you soon. This will be the last one this week, and we will be back with another Road to Notes session next week. So yeah, if you want to do more, register for this. Otherwise, yeah, thank you for attending. Thank you for joining here, and see you soon in another Road to Notes or other live stream. Thank you, Dave.
Thank you.
Bye.
Bye, everyone.